Okay, so for this matrix equation we just had then, our general solution will be x equals c1 x1 plus c2 x2. So that's c1. I'm going to write it in this vector form. 1, -1, e to the negative 2t plus c2, 3, 5, e to the 6t. Remember, when we're solving these homogeneous equations, any multiple of a solution is also a solution. So we had a minute ago, I claimed that this guy was a solution. Any multiple of that guy is also a solution. I could put a 7 in front of both of these. That's still a solution. It would still satisfy that original matrix equation. Any multiple of a solution is also a solution. The sum of two solutions is another solution. So the general solution is every possible multiple of the first guy plus every possible multiple of the second guy. Now, how do we know this covers all possible solutions? Maybe this guy was already a multiple of that guy and we're doubly counting and we're missing some stuff. We can't have this guy being a multiple of this one. So what we need is these two solutions need to be linearly independent. So our fundamental set must be linearly independent. And we check that using the Wronskian. Now it's a little different than what we had before because now we're in vector universe. The Wronskian of a bunch of vectors is simpler than it was back when we had like non-vector solutions. So x1, xn, all these vectors are linearly independent. That's the good version. If the Wronskian does not equal 0 identically, and the Wronskian is the determinant of you just write down all your vectors. So you just put them all as rows. You take every one of your solution vectors, write them down as a row vector in this matrix, take the determinant of that. As long as that does not equal 0, your vectors are linearly independent, which means it's not possible to multiply one of them to get another. They're not scalar multiples of each other, or if you have a whole set of them, it's not possible to add a bunch of these together to produce that one. What that means is they span the space. If you have R3, if you're in 3D universe, XYZ, a set of 3 linearly independent vectors would span the entire R3 space. You could get any point by adding multiples of those 3. So, for example, the vectors I, J, and K form a linearly independent, a fundamental set. They form a basis for this space because any vector, say I have the vector 5, 7, 9, I can hit that vector by adding up some linear combination of these 3. That would be 5i plus 7j plus 9k. Okay, so I'm giving you a little bit of linear algebra theory here as well. Okay, so let's check those guys that we just had. I claim x1, who was, what was he? E to the negative 2t negative e to the negative 2t and x2. What was he? 3e to the 6t, 5e to the 6t. I claim these are independent. Remember, independent is the good one. So to check that, we just check the Wronskian. Put this guy in row form, e to the negative 2t, negative e to the negative 2t, 3e to the 6t, 5e to the 6t. And I take this determinant. So we go that way minus that way. That would be, was that 3e to the 4t minus a negative, so plus 3e to the 4t. So we get 6e to the 4t, which is not 0. Oh no, I knew when I got that answer something wasn't right. I couldn't read my number right there. That's not a 3, that's a 5 right there. My arrow messed up my number. So this one should have been 5. And we get 8. Doesn't matter, it's still not 0. That's what's important. Vectors are linearly independent. So when I take a linear combination of them, I get the general solution. Okay, now a theory of how do we find the solutions. That was just checking a solution and checking if we have all the solutions. How do we find a solution? So if we have a linear, homogeneous system, so something that looks like what we just had. We don't have any +7s off at the end. Everything in the matrix or everything in the system is 5 times x plus 4 times y. There are always x's and y's there. Everything is, all the coefficients are constants. There are no sines and exponentials and so forth. Then we assume, literally just like we did in one dimension, our solution is of the form some k, that's a vector, times e to the lambda t. We assume our solutions look like this. Then x prime will be lambda k, e to the lambda t. K is a constant vector here. So taking the derivative, the lambda just comes down. But this is supposed to equal a times our original. So we get lambda k e to the lambda t equals k e to the lambda t. This must be true for all values of t. This guy is never equal to 0. Oh, I lost my a. So we get this equation. Lambda k equals a k. I really think linear algebra should be required to take this class, but it's not. You guys would get a lot more out of this class if you had had linear algebra. You would recognize what this is here. Matrices, when you multiply a vector by a matrix, in general, matrices rotate vectors. They rotate and rescale them. So if I have some vector, maybe it lives here, and I multiply it by a matrix, it's going to take that vector and rotate it and maybe rescale it. What this is saying, this equation says, hey, you got some vector, you multiply it by a matrix, it doesn't get rotated. It only gets rescaled. The answer is still in the same direction as your original vector. It's some multiple of your original vector. It just gets rescaled by this factor lambda. That's special. That means that this matrix, this vector kind of passes through that matrix in a special way. We call this vector an eigenvector of that matrix. And we call this number the associated eigenvalue for that eigenvector. So K here is an eigenvector. Eigen is the German word for characteristic. So we could call this a characteristic vector of that matrix. And lambda is the eigenvalue that goes with that eigenvector. Okay, so that's what we're trying to find, is that eigenvalue and that eigenvector. So we're going to do a little bit of matrix manipulation here. I'm going to move everything over to one side. AK minus lambda K must be the 0 vector. I'm going to factor that K out, but in order to factor that out, I have to stick in an identity matrix here. Otherwise, the dimensions don't match up. Lambda is just a number. I can't take a matrix minus a number. So in order to factor out that vector K, I have to stick in this properly sized identity matrix. If I have a 5 by 5 system, that would be the 5 by 5 identity matrix. Now, I can add together these two matrices, A plus negative lambda I. So this is the equation we want to solve. Well, the obvious solution to this is K must equal 0. The 0 vector. That's boring. We call that the trivial solution. We want non-trivial solutions. So in everyday math, in the real number system, we have something called the zero product property of equality that says if two things multiply to be 0, one of them must be 0. The zero product property of equality. This is what allows us to factor and solve quadratic equations. That property does not apply to matrices. Matrices do not satisfy the zero property of equality. Just because two matrices multiply to 0 does not mean one of them must be 0. There's another possibility. If this guy over here, this matrix is non-singular, then it can multiply by non-zero stuff and still spit out 0. And what do we mean by non-zero? We mean its determinant is 0 or non-singular. So the other possibility is this guy is special and has a determinant that's 0. That's what we're going to solve to find lambda.